Machine code or machine language is a set of instructions executed directly by a computer's central processing unit. Each instruction performs a very specific task, such as a load, a jump, or an ALU operation on a unit of data in a CPU register or memory. Every program directly executed by a CPU is made up of a series of such instructions. Numerical machine code may be regarded as the lowest level representation of a compiled or assembled computer program, or as a primitive and hardware-dependent programming language. While it is possible to write programs directly in numerical machine code, it is tedious and error-prone to manage individual bits and calculate numerical addresses and constants manually. It is thus rarely done today, except for situations that require extreme optimization or debugging. Almost all practical programs today are written in higher-level languages or assembly language and translated to executable machine code by utilities, such as compilers, assemblers and linkers. Programs in interpreted languages are not translated into machine code, although their interpreter typically consists of directly executable machine code. Machine code instructions. Every processor or processor family has its own machine code instruction set. Instructions are patterns of bits that by physical design correspond to different commands to the machine. Thus, the instruction set is specific to a class of processors using the same architecture. Successor or derivative processor designs often include all the instructions of a predecessor and may add additional instructions. Occasionally, a successor design will discontinue or alter the meaning of some instruction code, affecting code compatibility to some extent. Even nearly completely compatible processors may show slightly different behavior for some instructions, but this is rarely a problem. Systems may also differ in other details, such as memory arrangement, operating systems, or peripheral devices. Because a program normally relies on such factors, different systems will typically not run the same machine code, even when the same type of processor is used. A machine code instruction set may have all instructions of the same length, or it may have variable length instructions. How the patterns are organized varies strongly with the particular architecture and often also with the type of instruction. Most instructions have one or more opcode fields which specifies the basic instruction type and the actual operation, and other fields that may give the type of the operand, the addressing mode, the addressing offset or index, or the actual value itself. Not all machines or individual instructions have explicit operands. An accumulator machine has a combined left operand and result in an implicit accumulator for most arithmetic instructions. Other architectures have accumulator versions of common instructions, with the accumulator regarded as one of the general registers by longer instructions. A stack machine has most or all of its operands on an implicit stack. Special-purpose instructions also often lack explicit operands. This distinction between explicit and implicit operands is important in machine code generators, especially in the register allocation and live range tracking parts. A good code optimizer can track implicit as well as explicit operands, which may allow more frequent constant propagation, constant folding of registers, and other code enhancements. Programs. A computer program is a sequence of instructions that are executed by a CPU. While simple processors execute instructions one after another, superscalar processors are capable of executing several instructions at once. Program flow may be influenced by special jump instructions that transfer execution to an instruction other than the numerically following one. Conditional jumps are taken or not depending on some condition. Assembly languages. A much more readable rendition of machine language, called assembly language, uses mnemonic codes to refer to machine code instructions, rather than using the instruction's numeric values directly. For example, on the Zilog Z80 processor, the machine code 0000101, which causes the CPU to decrement the B processor register, would be represented in assembly language as DEC-B. Example. The MIPS instruction set provides a specific example for a machine code whose instructions are always 32 bits long. The general type of instruction is given by the op field, the highest 6 bits. J-type and I-type instructions are fully specified by op. R-type instructions include an additional field func to determine the exact operation. The fields used in these types are 655556 bits, op, rs, rt, road, shamt, funct, R-type, op, rs, rt, address, immediate, I-type, op, target address, J-type, rs, rt, and road indicate register operands. Shamt gives a shift amount, and the address or immediate fields contain an operand directly. For example, adding the registers 1 and 2 and placing the result in register 6 is encoded. Op, rs, rt, road, shamt, funct, 0, 1, 2, 6, 0, 3, 2 decimal 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, binary load the value into register 8. Taken from the memory cell 68 cells after the location listed in register 3. Op, rs, rt, address, immediate, 353868 decimal 00011 00011 01000 00000 00001 00010 binary jumping to the address 1024. Op, target address 21024 decimal 00010 00000 00000 00000 binary relationship to microcode. In some computer architectures, the machine code is implemented by a more fundamental underlying layer of programs called microprograms, providing a common machine language interface across a line or family of different models of computer with widely different underlying data flows. This is done to facilitate porting of machine language programs between different models. An example of this use is the IBM System 360 family of computers and their successors, with data flow path widths of 8 bits to 64 bits and beyond. They nevertheless present a common architecture at the machine language level across the entire line. Using a microcode layer to implement an emulator enables the computer to present the architecture of an entirely different computer. The System 360 line used this to allow porting programs from earlier IBM machines to the new family of computers, e.g., an IBM 1401, 1440, 1460 emulator on the IBM S360 Model 40. Relationship to bytecode. Machine code should not be confused with so-called bytecode, which is either executed by an interpreter or itself compiled into machine code for faster execution. Machine code and assembly code are sometimes called native code when referring to platform-dependent parts of language features or libraries. Storing in memory. The Harvard architecture is a computer architecture with physically separate storage and signal pathways for the code and data. Today, most processors implement such separate signal pathways for performance reasons but actually implement a modified Harvard architecture, so they can support tasks like loading an executable program from disk storage as data and then executing it. Harvard architecture is contrasted to the von Neumann architecture, where data and code are stored in the same memory which is read by the processor, allowing the computer to execute commands. From the point of view of a process, the code space is the part of its address space where the code in execution is stored. In multitasking systems, this comprises the program's code segment and usually shared libraries. In multi-threading environment, different threads of one process share code space along with data space, which reduces the overhead of context switching considerably as compared to process switching. Readability by humans. It has been said that machine code is so unreadable that the United States Copyright Office cannot identify whether a particular encoded program is an original work of authorship. However, the U.S. Copyright Office does allow for copyright registration of computer programs. Douglas Hofstadter compares machine code with the genetic code.